Now, so far, the main focus of what we have discussed was on aggregation basically step. And the reason for that is that in our aggregation step, we define how expressive our graph neural network is. Because if we briefly touched upon this in our isomorphism basically algorithm session lecture, and if we have a aggregation function that uniquely maps different inputs, different multi-set of embeddings into a different representations, we will get a graph neural network that has the maximal discriminative power. So meaning that if basically this graph neural network would be able to essentially learn different embeddings for different nodes, different unique embedding for different nodes, and it would be able to distinguish different two graphs that basically it's learning embeddings for those two different graphs. It can at most do as good as the test of isomorphism that we discussed, the Weisfeiler lemma, but that has some problems distinguishing some simple different graphs. But this is a problem that is still not solved, how to exactly represent two graphs in a manner that basically how to define a function that exactly defines two different basically representations for any two graphs that are not similar. So whatever that we have so far is kind of basically having some issues. Sometimes they generate the same essentially embedding, but that's the idea. We want to improve upon our aggregation step in order to have a graph neural network that, by our knowledge so far, is maximally discriminative. And we should basically call that the expressive power of our graph neural network. So because of that, the main focus so far on every literature that you look at is just to do some modification on the aggregation step. But that resulted in people just not looking at the update step that much. But there have been some basically ideas that people have developed for the update step as well. And that's what we're going to look at next. So one problem that is kind of unique to graph neural network is a phenomenon called oversmoothing. Now, when you have a graph neural network, when you have a neural network, just fully connected neural network, if you want that to be more and more powerful, you just stack more and more layers in order to make a more powerful, essentially, algorithm. But that doesn't really translate well to the case of graph neural networks. You can't just take different layers of message passing and add those into your basically network and expect that you have a more powerful, essentially, network. So, for instance, there's a model called graph convolutional network, and its maximum power is when it has only two layers. Anything about that, it will basically just deteriorate the basically node representations that it learns. And we will next look why this is the case. So let's say that I have this graph, right? So it has two nodes. I'm node 1 and node 2 that I'm gonna basically look at their embeddings. Now, we wanted to generate a graph neural network. In order to do that, we were constructing subgrid patterns with the height corresponding to the number of layers that we wanted to have, right? So node 1, it has information coming from 2, 3, 6. Node 2 has information coming from 1 and 3, right? And that's for a one layer of graph neural network, right? Now let's say that I have a two-layer graph neural network. And that's gonna basically be represented using a basically an additional layer of graph, basically neural message passing. In the first iteration, information from 1, 3 goes to 2. And then in the second iteration, information from 2 goes to 1, right? Same thing happens with every other neighbor that node 1 has. Information comes first to node 2 and then go to node 1, to 3, then to node 1, and so on and so forth, right? So this is the first layer, that's the second layer. And then we will have our final output, our final basically node level representation corresponding to embedding that we learned from this for this basically in this stage, right? So output of our second layer. Now let's look at this layer, this bottom layer. So this means that the setup node from which we are gathering information, right? We have two different graphs, a single graph, single random graph that I generated with Barber-Shelbert's random graph model that we'll basically discuss later in the course. But let's say that I have selected 3 different nodes that are seemingly in 3 different basically locations in this graph, right? So now I'm looking at neighbors of each of these nodes, right? And neighbors of this are these. Neighbors of this guy are these basically 7 points, and neighbors of this are this other 6 points. Okay, so far so good. Then these are the nodes. Let's say that if I'm defining a single layer of neural message passing, these are the nodes that each center node is gathering information from in a single layer, right? Then let's say that we have a second iteration. In a second iteration, that guy is gathering information from its 2-hop neighborhood, right? And I'm representing here its 2-hop neighborhood, meaning that itself, its neighbors, and neighbors of its neighbors, right? And I'm representing that for these 3, right? And then I increase that. I see that as I increase the number of my neural message passing layers, these basically red nodes are overlapping. These neighborhoods are overlapping each other. So for a K iteration of neural message passing, the K-hop neighborhoods are influencing the embedding at our node VI, and we are calling the set of K-hop neighborhood the effective range of that node in our aggregation scheme. So so we can quantify this basically influence using a score called influence score, and that's just summing over all the elements in a Jacobian matrix. So I have our embedding at basically for node I at K, which is our output that we want to basically generate. We have some input, right, at our first layer as inputs for every node, right? And these are, I gathered all basically, I have different neighbors within my K-hop neighborhood that are affecting my node VI, and I can quantify how much these are affecting, each node is influencing my final embedding by finding the partial derivative of my output embedding for that node I with respect to the embeddings, input embeddings for node J within its K-hop neighborhood. And then these 2 are just vectors of all ones. And when we multiply this, what happens is that it is just representing a summation over all elements that I have in this Jacobian matrix. Okay, I call this an influence score. And then I'm looking at a basically 4-layer, and I see that these 2 nodes, it's 100% overlapping each other, their effective range, right? So now what happens is that I'm constructing embeddings from this set of nodes, right? And as the set of nodes are overlapping, my features that I learned, the feature representations for the node, embeddings that I learned for each node become increasingly similar to each other. So I won't be able to distinct this after too many iterations of neural message passing. They're not distinctive anymore. And this is a problem unique to graph neural networks. So as a result of this problem, we call that oversmoothing, and we won't be able to stack as many of graph neural network layers as we want, as many of neural message passing layers as we want. And by basically when we have oversmoothing, we means that it is basically degrading our basically performance in different learning tasks, and it basically limits us in the number of layers that we can use. As I said, graph convolutional network is basically having its maximum performance with only 2 iterations of neural message passing. So one approach that we can take is by adding layers that extract information from the embeddings. So last session, we looked at this basically idea that before and after each message passing layer, we can pass the node embeddings through a basically linear layer, a basically single layer neural network. And through that, we can extract features from the embeddings that we have from the previous layers. Now, what we can do is to, instead of increasing the number of neural message passing layers, we can increase the number of essentially fully connected layers or whatever neural network that you're using to extract features from each node embedding, right? So we define a neural network, we pass basically all the node embeddings through this, and then we will have, so the idea, the goal is that we're hoping to have node embeddings now that are more basically distinctive, and we can better basically perform different tasks using these more distinctive and more expressive essentially embeddings. So that's one idea. Now, if you see, we have added more layers here, but the total number of neural message passing layers that we have has not increased. So that's one way to deal with this problem. Another way is to not basically do anything within each layer, but add neural networks before and after our graph neural network. So our basically neural message passing layers. So let's say that we have some input information to each node, and then we have 2 layers of neural message passing that learn node embeddings, and we're not increasing the total number of message passing layers that we have. Instead, what we do is before and after basically these layers, we implement some neural network. These are basically referred to as pre-processing layers and post-processing layers. So let's say that you have some basically input. So you implement some neural network, like fully connected layers over these that improve the quality of your embeddings. And then you just pass these to basically neural network, basically message passing layers. And then you have some output. Again, you can similarly do some post-processing on these. And that's essentially the second idea that we can use in order to basically overcome the oversmoothing. So again, these are called pre-processing, and these layers are called post-processing. Now, another basically way that we can deal with such problems is using the concept of skip connections. So let's say that in each neural message passing layers, we have 2 steps. We have an aggregation step and an update step. Aggregation constructs messages for each node using its neighbor embeddings. And we have basically the update that takes that and potentially takes the node's previous embedding as well, and combine this together in order to generate a new, basically, embedding, which is output of our neural message passing. Now, however, after a few iterations, this basically will kind of diminish the information that are contained within a basically the embedding of node I at iteration k will kind of get lost in after a few iterations of message passing. So what we can do to keep that is to kind of explicitly, instead of passing these into a function and kind of combine them, we explicitly combine them. So let's see basically what that means. One approach to do so is using a concatenation. So let's say that we have some aggregation function. Using this aggregation function, we have constructed a message. And then we have combined this message using basically update function with the previous embedding of node vi at layer k. Now, however, before basically declaring this as the updated embedding, we also concatenate the information HIK information, the embedding of node vi at level k with this updated value, and basically we consider that as our updated node embedding. Now we have explicitly added this to our basically new layers embedding. So we kind of keep trying to carry on this information without them being lost during the message passing. So concatenation was one way to perform this. Another way to perform this is using an interpolation. So for instance, here we have basically our update function, which combines these two together. So that's one side of the story. The other side of the story is the embedding that we have currently at that node. And we define some learnable vector. Basically, we call that alpha. And these values of alpha are between 0 and 1. And we use a Hadamard product to multiply this vector into basically our update and HIK. So we say that with kind of probability alpha, roughly speaking, it acts like a probability. With probability alpha, we have basically this, with probability 1 minus alpha. So it has this, right? But it's not probability, it's just interpolating. So it is saying that alpha, this alpha shows the share of the update, and 1 minus alpha is showing basically giving us the share of the previous embedding in the updated embedding of the node vi. So now, if you see, our alpha is going to be between 0 and 1, and what that means is that we are essentially interpolating between this update value and this HIK. So these are the two ends of one is basically a spectrum. And if alpha is all ones, we're gonna only get our output of the update as our basically updated node embedding. And if we have alpha equal to all zeros, we will just ignore the output of our update operator, and we will stick to the previous embedding of node vi as our updated embedding. Go ahead.
So in the update function,
in the what function?
The update function.
Okay.
So the hidden variables and the message functions, that message passing variables, are they concatenated or are they?
Can you repeat that? Sorry.
Oh, sorry. In the update function, we have two variables, the hidden parameters HIK.
Yes, and the message.
So how we concatenate them? Or?
So this is no. So I mean, these are two separate things, right? So previously, like last two sessions, we kind of considered different update equations. It can be anything that you define, right? It can be a concatenation. It can be, maybe a summation. I mean, if their dimension, yes, their dimensions match, right? So it can be average of these two. You can just sum these together. So there are multiple approaches. So that doesn't concern any of these two. We're saying that, okay, now whatever you want, update function, you just define it. And then we also want to explicitly add the previous layers, basically H. If you think about this, now let's say that this is k is equal to 0 and k plus 1 is equal to 1, right? So this vector is explicitly added to hi1. And then when I go to the next iteration, this hi1 is explicitly added and is included in hi2, right? So when you get to your output, it contains all the information basically that you have, right? So just to summarize what we have covered so far on enhancing our graph neural networks, we looked at graph neural networks as a basically few steps. We looked at it as an update equation, update operator, an aggregation operator, and then we said that these two combined together are going to construct our GNN layers. And then we said that in order to build a model, we're going to stack these GNN layers on top of each other, and that's going to give us a model. Then we said that we need to train this, right? So we're going to define an objective, a training objective for this model that takes the outputs of the previous layers, and it's going to basically compute some objective function, some loss function, in order to basically make some prediction. Now, then we looked at a few steps that we can take in order to improve our model. Those included in the aggregation and update steps. For the aggregation step, we looked at neighborhood normalization approaches that we're basically trying to ways that we were using to normalize the different functions that we're using to aggregate all the information from our neighbors. Like, for instance, just instead of sum, we were using the average or mean. So then we looked at set pooling methods, different aggregation methods like maximization, element-wise maximization, element-wise minimization. Then we looked at an approach called genosive pooling, where we were saying that instead of using a function that is invariant to permutations, this function is sensitive to permutations. And instead of just basically giving that as our output, we were summing over all possible permutations on this graph, basically on that neighborhood, in order to construct, and then we were averaging over all those in order to construct our message. Then we looked at directional biases, where for each neighborhood, we were learning coefficients, some basically attention coefficients for each edge incident to that node in order to see which neighbor is of higher importance for constructing the message for different nodes. Lastly, we looked at neighborhood sampling, where we didn't look at all the information that were coming to the node. We removed some of them, but then removing was just eliminating some information. So what we did was to have few iterations that were at each time uniformly selecting the nodes from the neighbor that we were getting information. That way, after a few iterations, we were basically integrating information from more neighbors. Then we looked at some issues with update method. The first one was over smoothing, which basically after too many iterations of neural message passing, we were just essentially getting the same basically feature vector for all the nodes. So we were losing the sense of local information for our output feature representations. We were looking at some approaches to overcome this, One was adding layers. So instead of adding more GCN, basically GNN layers, we were adding more basically MLP layers inside each GNN layer. Another approach was to add pre-processing or post-processing layers to our network. And next we look at skip connection, which was at each iteration explicitly adding the embedding from the previous iteration, previous layer to our output.